All right, welcome back, everyone. Ready for another deep dive. Today, things are going to get really interesting. We're going to be talking about machine learning models, but specifically the closed source ones, those where we can't actually see all the inner workings. How do we really know that they're doing what they claim? How do we verify their performance?
It's a great question, and it's becoming more and more relevant, right? Because as machine learning becomes more commercialized, these models are being treated like, valuable secrets, so their inner workings are kept hidden. And that makes it really tough to verify if those claims about accuracy, bias, or even safety are actually true.
Especially in areas where trust is crucial, like, say, a model being used for hiring decisions or by law enforcement. We really need to know they're working as intended.
Absolutely. Think about some of the cases we've seen where bias was discovered in production models, like the gender shades study. It showed that some facial recognition models were much less accurate for women, especially women of color, and that's a huge problem, right? That only came to light after the model was already being used.
Yeah, talk about a wake-up call. That brings us to the paper we're diving into today. It's called Verifiable Evaluations of Machine Learning Models Using zkSNARKs. Now, I know that title might sound intimidating, but stay with me. It's actually a fascinating solution to this problem of trust and verification, especially for those of you who live and breathe machine learning, data science, and math. You're going to love this.
It's all about finding ways to prove a model can do what it claims, even when we don't have access to the actual code.
And that's where these zkSNARKs come in. They're like this cryptographic magic trick, right? I mean, how else would you describe something that lets you prove you performed computation correctly without revealing the inputs?
It is kind of mind-bending when you first encounter it, right? But in this context, imagine being able to prove that a model achieved a certain accuracy on a data set without revealing the model's weights. That's what zkSNARKs enable us to do.
It almost sounds too good to be true. So how does it actually work? Walk us through it.
So the paper outlines a four-step process, and honestly, it's pretty intuitive once you get the hang of it. First, you've got to set up the model. The model being evaluated is converted into a format that works for these Z and X snark proofs. They use a tool called ESCL. You feed it a standard ONNX file, and it turns it into a circuit representation of the model.
Okay, ONNX I'm familiar with. It's like a common language for ML models, but circuit representation, what's that all about?
It's kind of like, think of it like a blueprint, but for the model's calculations. Every little operation, all the steps that make up the model's logic, are broken down into these tiny verifiable steps.
Ah, okay. So ESCL takes the ONNX model, makes this blueprint of verifiable steps, and then what?
Right, then you use that circuit to generate a pair of keys, a proving key and a verification key. Those are essential for this whole ZNS-SNARK magic to work.
All right, so the circuit's the blueprint, the keys are like the tools to create and verify the proofs. What's next?
The next step is all about choosing the data. You need a data set to actually test the model's performance on, and it makes the most sense to use a publicly available one. That way, everyone can understand and scrutinize how the evaluation happened.
Transparency is key. So we have our model as a circuit, our keys, and our data. What happens in step 3?
Now, this is where it gets really interesting. This is where the zkSNARKs shine. You run the model on the data set, and for every single input-output pair, you generate a zkSNARK proof.
Hold on. We're running the model,
There.
but we don't know the model weights, right? So how can we be sure it's running correctly?
And that's the beauty of it. The proof doesn't reveal the weights, it just shows that whatever the output is, it was actually calculated correctly using those secret weights. It's like saying, hey, trust me, for this input, this output is legit.
So each proof is like a mini guarantee, right?
Yeah.
But we're talking about evaluating a model on a whole data set. That's going to be a ton of proofs.
You're absolutely right. And that takes us to step 4. We got to bundle all those proofs, plus a hash of the model weights, into what the paper calls a verifiable evaluation attestation.
Like a package deal of proof that shows the model does what it claims to on the whole data set.
Yeah. And this attestation also includes a fingerprint of the model, a hash of its weights. So anyone can use the verification key to check that the proofs are valid and that they really do match the model that's claimed.
Okay, so let me see if I got this right. Even though those model weights are kept secret, we can use zkSNARKs to generate a package of proofs that verifies how the model performs on a given data set. And this package acts as a digital seal of approval, and anyone can use that verification key to confirm it's authentic.
You got it. That's pretty brilliant, right? And really important as more and more of these powerful models are kept under wraps.
It's incredible, but I have to ask, what's to stop someone from just faking this whole thing? making up those proofs and claiming their model's way better than it really is.
You're thinking like a true skeptic. And that's where the challenge-based model comes in. That's one of the more ingenious parts of this whole research. But I think that's a good place to pause. We'll dive into the details of that challenge-based model and some of the other really cool applications in the next part.
Sounds good. I'm already hooked. I can't wait to hear more about this challenge-based model. It sounds crucial.
Oh, it is. It's all about making sure the model being used in the real world is actually the one that was verified, but we'll save that for next time.
All right, welcome back. We're picking up right where we left off, diving deep into the world of verifiable machine learning. Last time, we were talking about zkSNARKs and how they can help us trust those closed-source models. We ended with a little bit of a cliffhanger. You mentioned this thing called the challenge-based model.
Right. That's really important because it helps us make sure those models stay accountable even after they've been evaluated.
Okay, so how does that actually work? What is this challenge all about?
Imagine you're using a model and you've got this verifiable evaluation attestation, right? You feel pretty good about how it performed initially based on those proofs. But models change, don't they? They can be updated, fine-tuned, or even swapped out entirely. How can you be sure the one you're using today is still the same one that was checked out in the beginning?
Yeah, it's a good point. Models aren't just static things in the real world. They're always evolving. So how does this challenge mechanism help with that?
It basically lets you, the user, directly challenge the model provider. You can be like, hey, prove to me you're actually using a model you claim to be using. But instead of just saying it, you do it by providing a specific input and then asking the provider to produce a fresh zkSNARK proof for that input.
I see, so I'm putting them to the test. But what's to stop them from just making up a fake proof, even if they are using a different model?
Well, remember how we talked about that proving key and that circuit being linked to the specific model? They can't just generate any old proof. They have to use the same proving key and circuit that were used to create the original attestation, the ones tied to that verified model's weight hash. If they try to use a different model, the proof won't work.
Oh, okay, so it's like a fingerprint. They can't fake it without the original model? That makes sense. But this on-demand proof thing, wouldn't that be computationally expensive? Especially if it happens a lot.
It can be, yeah. And the paper talks about that being a real challenge. They suggest a few solutions, like maybe the challenger pays a small fee each time they make a challenge, or maybe there's a reward system if they catch the provider using a different model. Sort of keeps things honest and makes the system more sustainable.
Clever. It's like turning accountability into a game. But this whole challenge thing seems most useful in real time. What if something comes up later, after the model's been used for a while? Can we still go back and check?
Definitely. In fact, the paper talks about how this can be used for something called post hoc audits. So let's say, down the road, someone notices that the model is producing biased outputs. Even if those specific inputs and outputs weren't part of the original evaluation, you can still investigate.
How would that work? Wouldn't you need the original data the model was used on? What if it's sensitive information?
You wouldn't need the original data itself. Remember, the challenge-based model just needs specific inputs. Like, let's say someone notices the model is giving biased outputs when given certain types of resumes, maybe ones that have certain demographic markers. You could use those same resumes to challenge the provider and say, prove to me that these outputs came from that model you claim to be using.
That's amazing. So even if issues come up later, there's a way to go back and hold the provider accountable. This is so cool. But we've been mostly talking about verifying performance, like accuracy. Could this technology be used for other things, like how fair a model is or how robust it is to different kinds of inputs?
That's a great question. And yes, actually, the paper does mention that. They say the same ideas can be applied to verify other properties of a model, not just its accuracy. Imagine being able to prove that a model treats certain groups fairly, even if you don't know the training data or what's inside the model.
That would be revolutionary. But how do you even define and measure something like fairness in a way that you can actually verify with these zkSNARKs? That seems much more nuanced than just checking how accurate it is on a test set.
It is more nuanced, but the paper suggests a couple of approaches. Like, you could set up specific fairness constraints based on statistical measures. Let's say you want to make sure that a loan approval model is approving loans at a similar rate for different groups, even if those groups aren't equally represented in the training data. You could actually turn that idea of fairness into math equations and incorporate that into this zkSNARK proof process.
Wow, so you're basically building fairness right into the verification. But it all sounds almost too good to be true. Are there any downsides or limitations to this approach?
Well, it is a powerful tool, but there are definitely limitations. One of the biggest ones is scaling this up to work with those really massive models, the ones we're seeing more and more of these days.
Yeah, like those giant language models with billions of parameters. I can only imagine how much more complex that would make things.
Right, exactly. The paper talks about how generating zkSNARK proofs, especially for large models, can take a ton of computation and time. Remember those proving keys we were talking about? For a huge model, those keys could be gigabytes or even terabytes in size.
Yikes. That's massive. It sounds like there are some serious hurdles to overcome before we can use this for those huge models.
There are, and the researchers acknowledge that, but they also highlight some really cool research that's happening that could help.
Okay, tell me more.
Mm.
What are people working on to make this more practical?
Well, one area is something called proof splitting. Basically, it's like breaking down the proof generation process into smaller chunks that can be computed at the same time.
So instead of generating one huge proof, you create a bunch of smaller proofs that can be verified separately, kind of like dividing and conquering, but for proofs.
Exactly. And that can dramatically cut down on the time and resources it takes. Another exciting area is GPU acceleration.
GPUs,
Yeah.
those are like the backbone of machine learning these days. I can see how they would be helpful here.
Absolutely. GPUs are built for parallel processing, right? They're already revolutionizing how we train and run those big models. And lastly, there's also a lot of interest in actually designing models that are inherently easier to work with for this kind of private inference.
Oh, that's interesting. So it's not just about making the proof generation faster, it's about making the models themselves more zkSNARK friendly from the
Yeah.
ground up.
Exactly. If we can design models with these privacy-preserving techniques in mind right from the start, it could make this whole verification process much smoother and more efficient.
I love that. It's like a whole new era of model design where privacy and verifiability are built in from day one. But I think we might have reached the limits of what we can cover today. There's still so much to discuss.
You're right. We've got a lot more to unpack, especially when it comes to all the different ways this technology could be used.
All right, listeners, make sure you join us for the third and final part where we'll be exploring some of those exciting possibilities. We'll be diving into the mind-bending concept of private benchmarks, which could totally change how we evaluate models, especially when we're dealing with sensitive data. See you there. All right, welcome back for the grand finale. We've been on this incredible journey through verifiable machine learning, and now it's time to see how it all comes together in practice. What kinds of models did the researchers actually put this system to the test with?
They actually tried it out with quite a few different models to show just how versatile it is. They started with some of the basics like image recognition using an MLP and a CNN on the MNIST dataset.
Ugh, MNIST. A classic. It's like the hello world of image recognition,
Yeah.
right? It's good to see they started with something well understood so they can show that the system works even for those foundational models.
Exactly. And to show it wasn't limited to just neural networks, they also tested it with some of those more traditional machine learning models. Things like linear regression, support vector machines, even a random forest. They used a smaller data set for these, but the point was to demonstrate that this approach isn't picky about the type of model.
That's important to highlight. It really speaks to the broader applicability of this technique. Did they try anything with generative models by any chance?
Yes. They tested a VAE decoder on the Celeba faces dataset. They wanted to show that the system could verify properties beyond just simple classification accuracy.
So they were able to prove that the VAE decoder, even with its secret weights, could actually generate those specific faces from the latent space. That's wild. It opens up all sorts of possibilities for verifying generative models, not just in terms of accuracy, but also things like how diverse or realistic their outputs are.
Precisely. And they didn't stop there. They even took on the world of language models. They tested an LSTM and a small transformer, that NaNoGPT model, on the human evil benchmark.
Wait, human evil, the one where models have to actually generate code?
Yeah.
So they were essentially verifying a language model's ability to write code. That's pretty impressive given how complex that task is.
It is. And it really highlights the potential of this approach to scale up to even those cutting-edge models that are pushing the boundaries of AI. Of course, as we talked about before, actually scaling this up to work with those massive models we have today is still a huge challenge.
Right, those models with billions of parameters. Generating proofs for those would be a whole other level of complexity. Did the researchers suggest any ways to tackle those limitations?
They did. They pointed to some interesting research directions. One is proof splitting, where you break down the proof generation process into smaller chunks that can be done in parallel.
So divide and conquer, but for cryptographic proofs.
Exactly. And it can save a ton of time and resources. They also talked about GPU acceleration.
GPUs, the workhorses of AI, they seem like a perfect fit for this.
Right. Their parallel processing abilities could be really useful for speeding up zkSNARK proof generation.
Totally. It makes a lot of sense. And then there was that third area you mentioned before about designing models specifically for efficient private inference.
Right. It's about more than just speeding up proof generation. It's about making the models themselves inherently more zkSNARK friendly. It would require us to change how we think about model architecture and optimization, but it could have a big impact on the efficiency and scalability of the whole thing.
That's amazing. A future where privacy and verifiability are baked right into AI models. What are some of the most exciting possibilities you see for this technology? What gets you really pumped up?
One of the most mind-blowing applications is the idea of private benchmarks. Imagine a company wants to prove that their model is really good, but they're using a data set that's super sensitive, something they can't share publicly because of privacy concerns.
Like, say, a healthcare company that wants to test a diagnostic model using patient data,
hmm
but they obviously can't just release that data to the public.
Exactly. With these private benchmarks, they could use zkSNARKs to prove how well their model performs on the sensitive data without actually revealing the data itself. It's like having your cake and eating it too. You get to show off your model's abilities while still protecting the privacy of that sensitive data.
That's incredible. It could revolutionize how we evaluate and compare models, especially in fields where data privacy is absolutely critical. And it's not just about benchmarks, right? You could use this for ongoing monitoring too, making sure a model is still performing well over time, even as the data changes.
Absolutely. It opens up a whole new world of trust and transparency for AI.
Well, I think we've officially reached the end of our deep dive. What an amazing journey it's been. We started with this challenge of verifying these mysterious closed source models, and now we're talking about a future where privacy and accountability are woven into the very fabric of AI.
It's a really exciting time to be working in this field. It feels like cryptography and machine learning are coming together to tackle some of the biggest challenges we're facing, and the possibilities seem endless.
It's truly inspiring. So, for our listeners who've been with us this whole time, what are the key things you hope they take away from our deep dive?
Well, first and foremost, zkSNARKs are a powerful new tool that can help us verify the performance of those closed source models, those ones where we can't see the code. And the best part is, it doesn't matter what kind of model it is, neural networks, traditional machine learning, generative models, even those cutting-edge language models, this approach can handle it.
And it's not just about verifying accuracy, it's about being able to verify all sorts of properties like fairness, robustness, even things we haven't even thought of yet.
Right. And while scaling this up to those massive models is still tricky, there's a ton of exciting research happening that could make it a reality. Things like proof splitting, GPU acceleration, and even designing models with these techniques in mind from the beginning.
And of course, we can't forget about the mind-blowing potential of private benchmarks, a future where we can evaluate and monitor models on sensitive data without compromising privacy.
It's a testament to human ingenuity, really. When fields like cryptography and machine learning come together, they can create some truly remarkable solutions to the challenges we face.
This deep dive has certainly given us all a lot to think about. And as always, we encourage you to check out the show notes for links to the research and resources we discussed. Keep those curiosity circuits firing, and we'll catch you next time for another adventure into the world of cutting-edge tech.